And I'm not going to do the demo. I'll do that next week for sure. Sorry, I know I'm a little sad too. I just forgot to bring all the stuff to the lecture room. We're basically killing snakes in Micro 2, trying to get the tilt tables wired up correctly, and adding an LM7806 to control the 7.2 volt battery so that it doesn't blow up our servos like it did last year. Anyway. So I will talk, on Monday we're going to do a little review for the practicum. So I will write the practicum over the weekend, so Monday on Tuesday, I'll know what we're going to do for sure, and I'll go over it in some detail and try and correct you for that. But I would encourage you, go ahead and make sure, after you do your lab on Friday, make sure you put on your Viva board a program that's going to blink your LED. Make sure your board is working. If your board's not working tomorrow, then come see me Monday. I'll be around a little bit tomorrow, late afternoon, and I'll be in lab briefly in the morning, like at 10 probably. But we're going down to the Duzin with the Epics folks, and we're doing that. So I'm going to be out of pocket for 2-3 hours in the middle of the day, so it'll be hard to track me down. But if your board's not working, bring it to me so we can fix it. I will fix it, promise. And if we can't fix it, we'll give you another one, and I'll solder it together for you. But I want you to have one, and I want you to get your 10 points. So if you bring a broken board and it doesn't blink the LED, you don't get your 10 points. So make sure your board works. And if it doesn't, then bring it to me. On Friday, we're going to use the standalone temperature sensor. I don't know if we'll do LM35s or not. I can't remember how many of these we have left. Students kept hooking up the power backwards and burning the snot out of them. So, and they're not super cheap, 50 cents a pop or something. But what I did, I bought a bunch of another chip, a similar chip from Microchip, and we put that on we put it on a little board, and that little board plugs into your A to D header. And so it's all set up, it plugs in just perfectly, it picks up power, ground, analog 1 and analog 2. So the only mistake you can make is to plug it in the wrong way. So try not to plug it in the wrong way. And just make sure that the power goes to the power and the ground goes to the ground. And the way the terminal's set on your analog header, which is right next to the end, then you have your 6-pin right angle header. So this has the little spots here. So this is 5-pin, that's a 6-pin right angle male, this is a 5-pin female, 6-pin right angle male, 5-pin female. This is the analog header, and it's labeled ground, power, and then there are 3 analog channels. AN something, I forget what it is, I can't remember off the top of my head. But, so it is AN 2, 3, and I'm sorry, AN 6, 7, and 11. And those correspond to RC2, RC3, and RB5, I think, yeah. So it's labeled on your board. I just have trouble reading it. But it's there. And so when you plug in the little board, I forget which way it faces, but the little board covers 4 of these pins. The 5th pin's not covered, I think, is how that's done. And there's 4 pins that plug in, and they should be labeled negative, plus, and then the 2 analog channels. Well, and so make sure you get those set up correctly. One of them has the little temperature sensor plugged into it, and then the other one has a little photoresistor. And so we'll talk about the photoresistor here in a minute. And there's also a resistor here, and there's a cap across the power and ground. So there's 2 little parts on, and the temperature sensor, which looks like a transistor, a little little TO3 transistor, whatever. And then you have the photoresistor, which doesn't look like anything except the photoresistor. I'll show you a picture of that in a second. And once you get this board plugged in, it's automatically all hooked up. If you plug it in the wrong way, it probably won't be the end of the world, because you won't have, the big problem is somehow powering these backwards. As long as you don't do that, you won't burn up the temperature sensor. The photoresistor is completely inert. You can't hurt it except stepping and crushing it, I guess, and even that's hard. So they're pretty robust. And the photoresistors are super cheap. The temperature sensors are, more like $1.50 a piece or something, so they're not super cheap. Okay, so that's what we'll do in lab, and basically you'll need to use the analog to digital converter to sample these two channels, one for the LM35 and one for the photoresistor, and then you'll also need to display that information on through the UART connection using the CR2102 and UART to TTL connector, or TTL UART to USB connector. So once you do that, you can open up a terminal program and you should display the temperature and the photoresistor. As you shine light on and off the photoresistor, you can figure out where a good threshold is, and you can actually set it up so that the photoresistor would turn on an LED or turn off an LED depending on whether it was seeing the light or seeing a shadow. And it's kind of fun to play with that threshold and kind of see how it works. It turns out photoresistors are very, they vary a lot, even within a lot number, all produced at the same time. They still have wildly different resistances. And we'll talk about that in a second. So anyway, so that's the lab for Friday. Okay, so let's see. I think. So let me talk about the photoresistor first, since we're kind of on that. So here's what it looks like. It's not very big. It's about maybe that big across, and it has this funny-looking pattern on it. It has two different electrodes, and it looks like the electrodes wiggling back and forth here, but actually it's one electrode interdigitating with the other electrode. And there's a clear top, and then there are two wire terminals bonded to the two electrodes. This is one electrode, that's the other electrode. And they're kind of interdigitating like that without touching. And this photoconducting material is applied over the top of this waffle pattern, so that there's a lot of surface area closely connected to the other between electrodes, so that you get a reasonable effect when it exposes the light and dark. It changes its resistance. Now, because this device changes its resistance, so you can think of it like this. It's basically a resistor like this. Well, so the way this is set up, it's kind of you have to set it up as a voltage divider for this to work. So of course it doesn't have, you can't dial this. And remember, when we did the pot, we had to connect both arms. We made this negative and this plus, and then we picked it off here and sent that to the A to D. Okay, and then as you change that, you change the reading on the A to D. So we're doing about the same thing with the photoresistor, only in this case we have a fixed resistance on one side, okay, and so we have a fixed resistance here. We're sensing this line, and then this is our photoresistor, and so this resistance changes based on light exposure. This resistance is fixed. And I think it varies. I think this is 10K, or maybe we did 50K on some of them, I can't remember. And then this varies from maybe 5K to maybe 600K, something like that. Totally dark, 600K, really bright, 5K. So you can see it's not going to go all the way from 0, as it varies, it's not going to go all the way from 0 to 3.3 or 5 volts. It's going to just do a part of that range. And so when it's 5K, it's going to be pretty close to ground, but not quite entirely. And then, say if we did 10K, then it would be like, it'd be about 1.1 volt or something. And then at 600K, then it makes this pretty much insignificant. So then it's going to rise pretty much to the 3.3 volts, something like that. So the range might be 1.1 to 3.3, depending on how we pick these values. And this is, and you can play with these values and try and figure out how to get it near optimum. There's a little equation for that. But in any event, because you don't really know what these numbers are for the photoresistor, it makes that kind of challenging. And like I said, in every batch, these things vary widely. So some photoresistors may work at one threshold, and others they may have a slightly different range. Okay, so this is what it looks like up against the quarter. You can see they're pretty small. They do come in different sizes, but and these things are really cheap. You can get 100 of them for a couple of bucks or $1. So they're used pretty extensively when you need to sense light, but the only drawback is that you do have to kind of set them up individually because the thresholds can vary dramatically. So I think I said dark 200 ohms, 200K here. I was talking about 600K. It really varies quite a bit. And the light resistance is maybe 5 to 10K. But there could be a 50% variation within the same batch. Now, there are other devices that sense light. So this is not the only one. There are phototransistors. In fact, almost every BJT will sense light if you take it out of its case and expose the silicon directly to the light. It will work pretty much as a phototransistor. And since they're active devices and you have to bias them, they can be made fairly sensitive. And then there are also photocells. Photocells that actually produce an electric current, produce a voltage with exposure to light, and if you complete the circuit, they'll source a certain amount of current up to maybe for a good sized cell, maybe a good good fractional part of an amp. So they can actually generate some power. And we call those photovoltaic cells. These we call phototransistors, and the thing we're going to use is a photoresistor. And there's some other things too. There are photomultipliers, there's a whole bunch of other stuff. So don't confuse all these devices because there's a whole bunch of them. There are a lot of different applications though. When you just want to have a sense of relative brightness, a photoresistor is a super cheap sensor to use. If you want something pretty sensitive, then you may want to go with one of these other devices. So we measure luminance. I'm not going to get into this because, frankly, until I review it every year, I'm kind of confused about it myself. But there are a whole bunch of different ways of describing brightness and luminance, and so lux is one of the units that's frequently used, and this gives you a little bit of a feel. And notice how this is very much logarithmic. I mean, this is quite from 0.002 lux on a moonless clear night sky, maybe up to direct sunlight 130,000 lux. I mean, it's quite a dramatic change. And amazingly, your visual system you're born with is able to navigate this whole range. Pretty impressive. And some of the cameras we have can do much greater ranges than this. How many of you have actually looked through real night vision goggles, like military style? Anybody here done that? It's pretty impressive. I've used them in the battlefield. I've used them flying helicopters at night, and it is pretty amazing. You can, it's like daytime. But if you go out on a night where there's a cloud cover and there's not a lot of light pollution and there's no moon getting through the cloud cover, it can still be incredibly dark. So night vision goggles won't work without a little bit of light. They need a little bit of light. And it's interesting, I remember in Ranger School when we'd be walking through the boondocks in the middle of the night and then the moon would come up, it was like sunrise. Just amazing. So a full moon can be quite bright once you're fully dark adapted and used to it. Yeah. So anyway, so that's it. So what else to say? I guess, so overcast day outside, 1,000 lux. Family living room, 50 lux. So these are kind of, put that in your brain. You kind of think, outside on a dark day, during the daytime, 100 lux. Inside, 50 lux. Moonless sky, 0.002 lux. So that's good to kind of general idea of brightness. Okay, that's all I want to say about the photoresistor. So you realize you can't get a reading out of it unless you put it in a bridge configure, or not in a divider relationship here. You must have this other resistor for it to work. Otherwise, if you took this out, you'd always read ground at that point, right? So it wouldn't help. Or you could connect that to VCC, you'd always read VCC. Wouldn't matter how much brightness. So you have to actually have it draw current and have a second resistor and read the divider point. It's the only way to do it. You can pick a different fixed resistor to give you a slightly different range. That's absolutely true. But you must have something there, otherwise you won't read anything. Okay, everybody good with that? All right. So I want to talk a little bit about some of the higher power devices. Oops. So one of the most amazing things, and I'll bring it in and I'll show you. I'll bring in a regular, desk light, and I'll hook it up to my PIC, and I'll turn it on and off with my PIC. I'll blink it with my PIC. I usually bring in a lava light just for the heck of it, but so maybe I'll do that. But in any event, our little bitty PIC can control large, powerful devices if you want. It's very easy. All you have to do is use a relay or a solid-state relay. And there are reasons for both, but generally speaking today, it's laziness unless if you use an old relay, that's just, I don't know, it amazes me. Most of the time, solid-state relays are just so much more reliable. It is almost criminal to design things today with old-fashioned coil and contact relays. And I'll talk about those a little bit because designing with these is not super easy. It's actually a lot more complicated, and there's a lot of reasons we want to avoid them. So obviously our GPIO pins can't drive high power devices. So we can't hook an AC motor up to your GPIO pin when your chip's running at 5 volts or 3.3 volts. In fact, you can't even hook up a DC motor to your GPIO pin for all sorts of reasons. The biggest reason is that your GPIO pin is limited to source and sinking 25 milliamps. And most motors don't do very well at 25 milliamps. And if you draw more power than that, then you'll heat your device up and you maybe burn out your pin. Obviously, you can't run AC devices on a DC pin. Clearly, that's not going to work. And oftentimes, even at 5 volts, a lot of the motors require a lot more voltage than that. Because motors and other high-power devices often have significant inductive loads, we want to be very careful not to cause these big spikes on our microprocessor when we switch on and off an inductive load. That's really a bad thing to do. So if you're driving a little bitty DC motor with your 5-volt pin and then you switch it off, you get a big back EMF effect that can actually generate a very high voltage spike on that pin and can actually cause major problems, and may very well burn out transistors connected to that part of the integrated circuit. So for a lot of reasons, we just don't ever connect GPIO pins to inductive loads, and we try really hard not to connect them to where we're going to draw excessive power. So we normally use another device to take our GPIO outputs and to turn it into the ability to switch higher power. The other thing is, oftentimes we have user interfaces connected to our micro so that the user can punch buttons and switches and stuff. And let's say we're using this to control a compressor on a refrigerator running at 110 volts. Well, we want to be really careful to provide isolation so that our consumer inputs are very highly isolated from the electrical characteristics of our heavy loads. So we don't want to get 110 volts on a touch button that somebody in their bare feet on a wet kitchen floor is going to run up and touch. So we want to have significant isolation, and we usually use opto-isolation to do that. How many of you are familiar with opto-isolation? Wow, okay. I thought you would all know this. Okay, well, okay, so I hadn't planned on talking about it, but it's worth a 10-second interlude here. So here's how an opto-isolator works. It's really very simple. We have a little thing. They're usually quite small. So physical size might be like this, okay, about that big or maybe slightly bigger. And on one side, we have often we just have an LED. And that's the arrow, supposedly. All right, whatever. And then it shines light across, and over here, we often have a phototransistor, a BJT, and driven by some circuit, and so it's biased in some way, and I forget, we've got something. And then we have this over here, and often this is often driving probably a FET. And so then this FET may be driving, some higher load. It's obviously more complicated than this, but the whole idea is that this circuit over here, which is your low voltage circuit, all it does is turn on this LED. And then light shines across a physical gap, an air gap, between these leads and the leads over here. And this air gap can, maybe it's a centimeter or so. That provides you a tremendous amount of isolation. To get a spark to fly across there, you're in the thousands of volts now to bridge that. So your opto-isolators typically give you maybe 10,000, 20,000 volts of protection here, which is really nice. Maybe not that much, but it's quite a bit. And it might even be in a vacuum, all the better, where it can't ionize something and jump across. So, and it's usually all sealed up. So all you see are the leads coming out. And this is a very nice thing. The amount of current that it can handle on this end, of course, driven by what kind of FET or BJTs are used and how that's hooked up. And we'll talk about that in a minute. But so often we do this opto-isolation to create this nice air gap between our low voltage circuits and our high voltage circuits. So here's off the data sheet for your PIC 16F1829, and you can see we do have these chips. I've actually one of the things that's kind of interesting is what level. So when we have, let's say this is your circuit right here, okay, and you have a pin. Maybe it's PTA5 or something like that, or RA5, I guess we'd call it, RA5. So let's say it's RA5, or whatever it is. What if we want to sense a 0, or we want to sense a 1? What are the actual voltages that we have to put into that pin in order to sense a 0 or a 1? What are the actual limits? Well, what do you think? What are some things we have to take into consideration when we look at those limits? What's that?
3.3 volts.
Okay, so you kind of stumbled into one of the answers there. So what is our VDD? What's the voltage we're running the chip at? That actually has a lot to do with what the levels that define zeros and ones are. It also turns out we have a register that changes the function of these inputs from TTL to SMIT trigger. And SMIT triggers have a different level. So we have to go to the data sheet. So here's the data sheet. And look at this, kind of interesting, right? So there's a couple of lines. We have special lines when we hook it up for I2C. We have to have pull-up resistors and stuff like that, so we don't worry about this. And then there's an SM bus levels, we're not going to worry about that. And then the master clear and a couple of other things, and so forget that stuff. What we're really interested in are the two lines. TTL buffer, which would be the standard output, and SMIT trigger, which is one of the selections you can make. And that's true for the input, and that's true for the input low voltage and the input high voltage. So the line we need to look at is TTL, and it takes these two lines. And notice, if our VDD, if we're running at a VDD between 4.5 volts and 5.5 volts, then we define a 0 as anything 0.8 and lower. If we're running between 1.8 volts and 4.5 volts, such as 3.3 volts, now what we define as a 0 is anything equal to or less than 0.15 VDD. Oh, well, what is that? Well, so we get out the trusty calculator and we'll crank it out. So I'll do it. You guys can do it too if you want. So let's see. So we're running at 3.3 volts, and so we have to multiply that by 0.15. So it turns out 0.495 is the definition of a 0, 0.495 and below. So if you have it programmed, if you have it also, maybe you have some kind of a sloppy switch, and I don't know. Anyway, it doesn't quite get it all to 0, or maybe you're using a weak pull-up and it can't quite overcome that or something. I don't know. But anyway, you have to make sure you get your voltage on that pin below 0.8 volts in this range, or 0.495 volts at 3.3 volts, in order for it to be defined as a 0. So, and then what about the high voltage? Well, from 4.5 to 5.5, it's 2 volts, and then from 1.8 to 4.5, it's 2.5 times VDD plus 0.8. So you do that calculation. And then if you switch it into Schmitt trigger by setting one of the bits in the register that controls that output levels, or sorry, input levels, then this is the formula you have to use. It's going to be 0.8 times VDD, or it's going to be 0.2 times VDD for the low, 0.8 times VDD for the high. So sometimes you have to get down in here and actually think about these voltage levels depending on what's going on and you know, how you're driving these inputs. If you want to make sure that your input is definitely recognized as 0 when it's not absolutely 0, or a 1 when it's not absolutely VDD. All right, any questions about that? Everybody should kind of know that. Yeah?
So there's gaps, like for the input low, what happens between 0.8 and 2 volts?
So in that case, it's going to be indeterminate. Probably what will happen is if the pin had previously recorded a low, it'll continue to sort of see a low, and it won't switch it off to high until it gets up over 2.
Okay.
But you can't count on that.
Yeah.
And that's definitely that would just leave you hanging, not sure. Yeah.
That's great.
So, and then we have some other electrical specifications here as well. So, one of the things that's interesting here, let's see, total power dissipation, 800 milliwatts. And so, maximum current out, VSS, 85 milliamps. Maximum current in, VDD, 80. So notice that you can sink 85 milliamps out of VSS, but you can only source into the chip 80 milliamps. And that's one of the reasons why we typically like to sink currents and not source them with our GPIO pins when we're using them as outputs. So, but both the sink and source limits are 25 milliamps. But you get if you sunk everything, you get another 5 milliamps on your total budget, because your budget on your VSS pin is well, yeah, that is 85 milliamps instead of 80 milliamps. And it also you can see, but it's you can see as temperature changes, it's quite a bit different. This is for the extended commercial temperature range of minus 40 to 125. Anyway, so our part is the standard 40 to plus 85. All right. And there's also an interesting relationship between how much power what your voltage drive of the chip is and how fast you can run it. So if you really want to run at 32 megahertz, you have to be at least at 2.5 volts for VDD or above. So at 3.3 you can run it at any frequency, but once you drop below 2.5, like at 1.8, you can't go over. For a typical LED is about 20 milliamps. And so you have to keep this in mind, but notice the current limiting resistor you choose is somewhat driven by what kind of LED you have. So on red, green, yellows, they have a voltage drop across them of about 1 to 1.5 volts. But on blues and whites and some of the weird colors, they can drop as much as maybe 3.5. So at 3.3 volts, you might not even be able to drive them, although for some reason that never seems to be a real problem, even though some of these values are sort of published and talked about. But so I think it must really be less than this for most of those. Our RGB LED seems actually to be pretty reasonable, but the blue color is not as it's not as bright and not driven as robustly as the red and green. And probably what we should do is have a slightly lower value resistor on the blue color than we do on the other two, but I didn't do that, although we could. I just haven't done that. Okay. Yeah. All right. There are some really amazing uses you can use with your GPIO pins. You can bit bang interfaces that aren't supported, so you don't have a module to do maybe, I don't know, UART or I2C or something. You can bit bang those interfaces. It's a little challenging, but you can do it. You can kind of create your own module and software. And you can emulate most protocols. And then there are quite a few protocols that normally don't have modules built in for them, like the NEC infrared protocol used with many, many remote control devices. Yeah.
How powerful is our chip?
You mean in terms of what?
The world, the industry?
Well, so it's definitely a low-level chip. It's an 8-bit chip. The clock's pretty fast. The instruction cycle's not bad. And it's got 8K of flash and 1K of RAM. So it has a fairly good capability. There are a lot of chips with less memory. You can buy micros with 128K of program memory. I'm sorry, with 128 bytes of program memory. You know, a little bitty program memory, because maybe you don't need that much. And you do save money when you buy them. And I think I mentioned there are transistors for sale in China that are kind of, you know, knockoff, no-name things, and you can buy those for less than a penny a piece in many cases. It is crazy how cheap they can be. So, and some of them may not have that much memory, but maybe you're going to put it into a toy to do a very simple thing and you don't need that much. Yeah?
So on that same note, for any microcontrollers that you have in, say, a new car, about how powerful would those be? How much would the car
So that's a good question. So for starters, I don't know if you guys have had this experience, but in my Lincoln, on my map, when my fuel drops below a certain level, my map shows me where every gas station it has in its database is. I can barely even read the map because of all the gas stations it shows. And then as soon as I fill the tank up, that goes back off. Now, what does that tell you? That tells you that the micro that knows how much gas is in my gas tank can talk to my radio and my map screen. That's it. Does that surprise you? Every micro in the car is interfaced to every other micro on a CAN bus, typically, although there are other buses used. And so you at least have to have a micro, you know, hot enough to implement CAN bus. That's just for starters. But it then depends on what it's going to do. If all it's going to do is put your windows up and down, or PWM your seat heater or something, then it may not have a whole lot of horsepower. But then ones that are running the entertainment system, and mine, I can put a CD in, I can burn the CD to my built-in disc. Well, I can rip it. Yeah.
Still impressive.
Yeah, I don't know how many CDs it'll hold, but a whole bunch.
My car has radio.
Well, mine's not as fancy as some, you know, it's a 12 Lincoln. It's actually got a nice entertainment system, but I mean, it's, you know, it's not the end of the world. It also has satellite radio and all that, you know, and it's amazing, all that implemented. And I'm sure inside of that, there's probably several processors, but the one that's controlling that system talks on the CAN bus to all the other processors. So the one that's adjusting the ignition in the engine, and the one that's doing the throttle position sensing and the oxygen sensor and, you know, all that, they're all talking. And it's amazing. And even somebody's talking to the little transmitters in the tires that tell you what the pressure is. It's crazy. So they're pretty robust. I mean, they're not like, they're probably at least as powerful as the one we have. Our chip doesn't have a CAN module. So they're at least fancier than that. But on the other hand, there are chips in our family with CAN modules.
Wasn't there a version of our chip that was made for automobiles?
Yeah, it is. Yes, the LIN, and it's got a CAN module. Yeah. So, and I'm sure it's out there in a number of automobiles. But the KL25Z chip we'll use at the end of the course is out there in a bunch of automobiles too. And then ones that are, you know, ones that are taking my side radars and detecting cars in my blind spot, they're fairly sophisticated. But and now they're actually producing those on the same piece of silicon as the radar circuitry itself. It's system on chip. So on one little bitty thing, you have your entire radar system done. And then it just sends it's whatever, you know, parameters it needs and what information it's getting back to some other system. Pretty amazing. All right. So one of the things that we can do is do open collector output. Now this is used completely in I2C protocol, and the ports on our chip that can run I2C are configured so that when you put them in I2C mode, those pins become open collector outputs. That's how they work, and then you can also detect the input, so you can monitor the input and their open collector output. So they're bidirectional. And the way this open collector output works is the collector is left unconnected. It's just connected to the wire. So when you want to send a 0, you drive the base and you pull the collector down to ground. But when you want to send a 1, you just turn off this transistor and let the collector float. And what happens is you must install external pull-up resistors to make this work. And you have to size those resistors so that it pulls up fast enough to support the data rates you want to send. So at 100 kilohertz, you can use a smaller pull-up. You can use one with a smaller resistance, a bigger value resistance. And then when you want to ramp the data rates up, you have to decrease the resistance a little bit so that it pulls up faster, because there's always some parasitic capacitance on these runs. And so anyway, what's nice about the open collector, though, is it gives you the ability to hang a whole bunch of peripheral devices on the same bus. Since all the devices you put on this bus are open collectors, when they want to listen, so they're always listening on the bus, okay? When they want to assert information on the bus, they do it by pulling the bus low or releasing the bus and letting it get pulled high by the pull-up resistors. So none of the devices on the bus ever drive the bus high. As a result, no two devices ever create a short circuit where high current flows, because no device is driving it high and another device pulling it low at the same time. There are devices that are fighting each other. One's trying to let it float high with the pull-up resistors, and another device is pulling it low. Well, the one that's pulling it low will win, and the other one senses that and backs off. So that's how you can have multiple masters on the I2C protocol. But the nice thing is you can hook up all these devices, and you don't have to turn the chips on and off and have tri-state buffers on the outputs of the chips. You can let these lines be fully bidirectional if you need to. So even the clock line on I2C, so there's 2 lines on I2C, the data and the clock. The clock line's out there ticking away, the master's running that. But the slave can take the clock line and hold it low. And the master's trying to let it float high, but it doesn't float high. And the master goes, oh, son of a gun, one of the slaves has pulled this sucker low, meaning that it's trying to stretch the clock a little bit because it's not fast enough to respond to the rate that I'm using. So I'm just going to patiently wait until that slave lets it go, and then I know it's good to continue. And that way your slave can slow the clock down a little bit if it actually has to do that. So it's really a pretty cool protocol in that regard. Whereas there's no mechanism for that in SPI. On the other hand, SPI runs in megahertz ranges, and I2C runs in kilohertz ranges. So it's, it's all, there's pros and cons. But this open collector interface is a really nice way to have bidirectional buses implemented, but they're not as fast as fully driven buses. The only problem with fully driven buses is you must tri-state anything that's supposed to be listening and not sending. Because you can't have them driving, you can't have two people driving the bus, one high and one low. That's a short circuit. And you'll have really high current flows. So that's how the I2C protocol works. It has, both lines are driven with open collectors on the master and the slaves. We can also use standard BJTs as nice digital switches. And we often, if you don't need to switch much power, maybe 80 milliamps or maybe as much as 100 or a little over, you can definitely get a BJT that'll do that just perfectly for you. And you have to set these up though, because you want to choose the right device. So it turns out one of the things you have to always think about when you do high-powered devices, you always have to ask yourself the question, am I going to switch the high side of my load, or am I going to switch the low side? Now somebody tells me, what does that mean? What does that mean?
Are you going to send current to the device, or are you going to sink it from the device?
No. So let me draw a picture and then you can kind of think about it again. That's a good idea, but not the idea I'm looking for here. So when we let's say we have a power supply here, and we have and we want to switch it. So here's let's say here's our load, okay? So there's some power going to the load, and the other terminal's grounded. When we talk about switching the high side, we're talking about putting a switch in here. When we talk about switching the low side, we're talking about putting a switch in here. Now, what do you think you want to do? Most of the time, where do you want to put your switch? How many think you want to put your switch in the high side? All right. How many think we want to put the switch in the low side? And how many are too busy on their cell phones to give a care? All right. So this is good. I want you to think about this. This is something you need to learn, because you're going to have to, unless you just never touch an electronic device the rest of your life and you type code, and even then you might need to know this. So let's do this again. Everybody participating, okay? Put the cell phones down for just give me a minute, okay? 1 minute, that's all I'm asking. Okay, how many think you would want to switch to the high side? Raise your hand. How many think you want to switch to the low side? Okay, you want to switch the high side. Now, here's the question. Why? Well, let me just say, for sake, let's take a car, okay? So let's take a car. Well, no, let's not take a car. Let's take a house, okay? So let's say we have so here's your power. So in a house we don't use DC, we use AC, but it's the same idea. One of the lines is hot and one is neutral, right? So we talk about the line and we talk about the neutral. I think that's how it's spelled, neutral. What? Okay, well, how I don't know. I don't know. Look, I never said I get spelled. I know I'm good at that. Okay, so here's the high side, and here's the low side. Okay, now let's say we have, I don't know, let's say we have a light, okay? So here's our light, and we have a little thing here, and then we're down here. Now, obviously, this is gonna turn on and off. Now, let's say we put the switch down here, okay? Now, let's say you're changing the light bulb. You turn off the light, and then you get up in the ladder and you're unscrewing it, and you're not being super careful, and your hands get on the base threads of that bulb. It's hot. You're in trouble. You're probably going to feel a nice little zap and fall off the ladder and break your neck. So you would really want to switch it up here, wouldn't you? Right? Because now the device, it's grounded, but it ain't hot. And that's why we normally want to switch the high side. But here's a problem. The problem is that a lot of times we build these switches with solid-state devices. And these solid-state devices, we use field effects transistors. And I always have to review this to get it right, because I don't design with these parts day in and day and night. But you have, remember you have this floating channel here, and I always forget which way the arrows go. It's kind of backwards to what I would have thought. So I don't know. But anyway, we'll say this is, I don't know if it's an N channel or P channel. I forget with the arrows. So here's the deal. Remember, the gate's totally floating in this case. But in order to fully turn this on, you have to bias it correctly. In order to fully turn it off, you have to bias it correctly as well. And for N-channel devices, to fully turn it on, you have to take this up higher than the high side. But where do you get the voltage to do that? Because that's your high side. So if you're going to use an N channel in the high side, well, I didn't explain. So we normally want to use N channels. Why do we want to use N channels? Well, we want to use N channels. So if you use the P channel in the high side, everything works fine. Because then you just have to go down here and everything's great. If you use the N channel in the low side, everything's fine. Because you don't have to go, you can go way above where you need to be here to turn things on and off, and everything's fine. But when you want to use an N channel on the high side, now you have a problem. Because you've got to have a voltage higher than the high side in order to fully turn it on. And so to get that voltage, you often have to do charge pump devices and all sorts of things. You can do bootstrap capacitors, and you can play games, or a secondary power supply. But it's not easy, and it's a pain in the butt. Why do you think you want to put N channels in the high side where they don't really fit instead of a P channel? Why would that be the case with a FET? Why do you think that might be true? Unlike a BJT. In a BJT, you can use a P channel up here just fine. I mean a PNP up here and an NPN down here. That's great. But a FET, which is a little better. Well, so what's the difference between? So what do we use with really high power? Do we use FETs or BJTs?
We use, I think we use FETs.
How many think we use FETs for high power? That's right, we do. Why do you think we do that?
The material it's made out of, probably.
It has to do with on-channel resistance. And the on-channel resistance, and it also has to do with BJTs, the way they're built. A BJT always drops something like 0.7 volts across its junction, always. You can't get away from that. Whereas the drop across a FET may be very, very, very small. And in fact, we talk about it not in terms of a fixed voltage drop like we do with a BJT. We talk about it in terms of an on-channel resistance. The on-channel resistance of a good N-channel FET is down in 0.010 ohms, okay, or 10 milliohms. Whereas a P-channel FET is probably going to be more like 150 milliohms. So it's dramatically more. And for high-powered devices, that's heat. That's heat. That's voltage drop and heat. And so you can't take too much of this in a high-powered device. It's going to cost you. Whereas here, much less heat, much more power can go through. So that's really what drives that. So oftentimes with H-bridges, we play these games. We have built-in charge pump devices. to use N-channel FETs in both the high side and the low side. But using BJTs, it's fine because they're going to drop 0.7 volts no matter what you do, so it doesn't matter. And as long as you don't put too much current through it, you can handle that. But if you put a lot of current, the 0.7 voltage drop is going to give you a lot of power, a lot of energy wasted. We're going to use in lab, not this week, but next week, I think we're going to do the BJT lab, and we'll use two N3904s and a 3906. And I think they can get somewhere around 200 milliamps, although actually it's more like, I think it's more like 150 or 90. They get kind of hot. So the really nice thing, is that you can switch higher DC voltages than your processor's running at, and it can definitely, if you want to drive a bunch of different things with the same pin, it can definitely increase that fan out. And it gives you a little measure of extra protection for your microprocessor pin, and they're cheap and they're small. Lots of good reasons. A couple of things to bear in mind. So there are two ways you can implement a high side switch. So notice here, the resistor here is our load. Here's VCC, here's ground. So notice here we put our switch in the high side in the form of a BJT. And here we're using a PNP in the high side. Here we're using an NPN. Now in this case, this is not a good idea because our control current, well, so in order for this to turn fully on, you must have current flowing in the base. Is that true for the gate in a FET? No, the gate is completely insulated and almost zero current flows, just a little bit to charge up its parasitic capacitance, and then no current flows. And in fact, once you turn a FET on, you can cut the wire to the gate and it'll stay on forever until you short it to ground to get the charge off of it or drive it high or whatever you have to do to change the channel. But in this case, in order for this to be on, you must be drawing a current through the base and out the emitter. And in this case, that current is also going through the load, so changes in the load can impact your bias and your desire to fully turn this on, and it can kind of screw your circuit up a little bit. So you don't really want the load involved in that. Over here, the load's not involved in it at all. Notice here, the current flows through the emitter, out the base, fully turns this transistor on, but none of the base current goes through the load. And that's why we want to use a PNP in the high side, and then when we're switching the low side, we want to use an NPN. Whereas in the low side, a PNP is a bad idea, and in the high side, an NPN, you know what I mean. So anyway, that's because there has to be current flowing in that base. But in the case of the FET, it's a different thing. We want N channels wherever we can get by using them. If you can tolerate a little higher channel resistance, then you can use a P channel in the high side, and that's okay, because then it makes your interface problem easier. You don't have to have some kind of fancy way to create a higher voltage than your source. But and that's the other thing. Imagine this drive up here is like, it could be 24 volts, right? Where your micro's running at 3.3. But if this is a FET, you've got to get this above the 24 volts to fully turn it on. Significantly above, maybe 5 or 6 or 7 volts above it. So you have to have some fancy way of doing that. You don't need much current. You just need a little teeny bit of current. But you have to get it up above there in order to fully turn it on. And if you don't fully turn it on, the channel resistance will still be significant and it'll burn up your part. All right. So so remember, you want to do PNP in the high side, NPN in the low side for BJTs, but N channels on both sides typically for FETs. And then sometimes we use two transistors to make sure we get ours fully turned on. It just makes the biasing issues simpler. And then this is a nice, robust 2-transistor switch, and this is what's on your Viva board. So sitting there on your little Viva board, you've got that green terminal. One terminal is grounded, and the other is connected to this transistor that's connected to your battery. Directly to the battery, not to your VDD. And then you have a 2-pin female plug here, and if you drive this high, it'll turn on this transistor, which will turn on this transistor, which will cause current to flow to your load if it's connected out here. And it'll be battery voltage, not 3.3 volts or 5 volts, unless that's your battery voltage. And the nice thing is there's good isolation here, so you're very unlikely you're ever going to have a problem with your micro pin. Very little current has to flow to do this, but a little bit does. Anyway, and feel free in your project, if you need to switch a little bit higher voltage, or you're going to put a little buzzer and you want to make it louder, you definitely can connect it to this green terminal and get 9-volt battery power running through it instead of 3.3 or 5 volts. Okay, it's just a more robust. Let's talk a little bit about mechanical relays. Turns out these are actually a major source of failure. I don't know, how many of you own a house? Okay, how many? Some people do. For those that own a house, have you ever woken up on a cold winter day and the house was really cold and you realize your furnace wasn't working? Or hiring snot in the summer and you realize your air conditioner was out?
Oh, that happened.
There you are, happened in the apartment. So, now, there are a myriad of reasons why that can happen. But most of the time, not all the time, most of the time, it's because some controller board driving your operation goes out. And most likely, that controller board has about 10 relays on it. Little bitty, tiny relays, and one of them stopped working. That is like the overwhelming most likely reason. I mean, your compressor can fail, you can run out of Freon, I guess there are a lot of things, but whatever. But normally, but there's a lot of failure with mechanical relays. And they also make a lot of noise. When you design with them, you're actually required to have minimal current flowing when you break the contacts in order to cause a teeny little arc to keep the contacts clean. And if you don't design it with that minimal current, or you have the wrong level of current or whatever, and you break the circuit, you may actually get the contacts corroding much faster. In addition to that, every time you open up the drive to the relay coil, there's back EMFs. So you have to put quenching diodes in to help with that, but even so, you're getting spikes on all your lines, which can get into your logic and can definitely affect any integrated circuits you have, including your microprocessor. And then eventually, every relay will fail. It's just a question of when, not if. And but the nice thing about relays is reactive loads are handled with total grace. They don't care about reactive loads because it's just a mechanical switch when it's all said and done. And it looks like this. There's a coil that pulls this arm, and the arm pushes this spring lever, and it pushes this up and makes a contact. And oftentimes they're set up so when it pushes up, there's another contact down here that it breaks. And so often there's multiple contacts all on the same relay. There could be a whole host of different switching arrangements. But it's something like this. And of course the coil is where you get the reactive load. This is what a lot of them look like. And if you go up and look at your furnace or air conditioning control unit, you'll see a bunch of these little plastic boxes soldered down on the printed circuit board running that thing. And you'll find that these are typically double pole, double throw, fairly low voltage. They typically are switching. Often they run at 5 volts or maybe even less with maybe 80 milliamps. They can often understand big voltage surges, and they can often handle significant currents. 10 amps, no problem. At 277 volts, pretty easily. So these are nice little devices, but you can also use these instead. These are solid state relays, and they can take an input signal. Let's see, this is maybe a bad example. This is running on 90 to 280 volts, but normally most of these will run on, I have a whole bunch of them that you can drive with 2 volts, 3 volts, or 3.0 volts and greater. So 3.3 will drive it fine. And it's optically isolated from the other side. And the other side can be 440 volts, 240 volts, 25 amps. they can carry some really significant currents. And so these are really not a bad way to go. There's no reactive load. Well, there's no switch coil in here, so they don't have noise. These are usually implemented with a bunch of FETs, and they're optically isolated. But they are isolate optically large voltages from your sensitive electronics and user interfaces. So, and typically the solid state relay looks like this. You typically have a little opto isolator here, and then there's a big driver circuit, and then you have these big field effect MOS transistors that drive the load. So there are some other things out there. There are thyristors, silicon-controlled rectifiers, and they typically are used for these AC solid-state relays. And then for DC solid-state relays, we typically use big, strong MOSFETs. Okay, so let's see. Like I said, because we want to typically use, in the DC circuits anyway, we typically want to use N-channel FETs on both high side and low side. We often will have to have some kind of a charge pump circuit in order to really turn fully on the FET and also to turn it off rapidly. There are some of these AC circuits where they get switched off sort of automatically at zero crossing, so when you want to turn it off, you may not be able to turn it off until it gets bound to the zero crossing point. All of these things do have a little internal resistance, so they all take a little power. They aren't as low resistance as a relay contact would be, but then a relay has a coil that has to take a little power for it. But when you're running really large powers, a lot of times, there may be a time when a relay's could be the best thing to do, but most of the time you can do it with a solid state relay. All right, so advantages of our solid state relays. So they're often smaller than relays. They often, they don't make noise, they don't bounce, they don't arc, so you can use them in explosive gas areas. They're not very sensitive. They're not sensitive to mechanical shock. If you take a regular relay and you bang it real hard, a lot of times you can vibrate those contacts and actually make contact briefly. That can be very bad. So we had our microwave oven when we lived in Ohio caught on fire when one of my daughters slammed the door of the microwave oven, and it bounced a relay and fired it when it shouldn't have. And I mean, it went crazy. And it caught on. I mean, we had to unplug it and drag it off the counter so it wouldn't burn the house down. Yeah, it was shocking. And then, yeah, well, the first thing you do is unplug it. So you can use very, very small control voltages and currents. Unlike relays, relays take a good healthy chunk of current, like 80 milliamps, kind of at the bare minimum. It's rare to find one you can drive directly from a GPIO port without a BJT in between it. And then humidity, strong magnetic fields, long storage times do not affect solid state relays. They definitely affect regular relays, and it can cause them to completely corrode and fail. The downside, though, when there is always a little bit of heat generating when they're on, and there can be some junction noise, but there's no inductive noise. I think in the end they're much less noisy. And then their voltage and current characteristics are not perfectly linear, so that's a little bit of an issue. And then there can be glitches, but there's no bouncing. So really, I think it's a win overall for sure. Relays tend to fail open, but solid state relays tend to fail short, which obviously is less desirable. And then you can't switch them as fast. I mean, you can't switch relay. You can switch them faster than relays, that's for sure. But their break time may not be quite as fast as for a relay. The relay can break really fast. Whereas there's a certain amount of body diameter recovery time and stuff to get a FET to break. And then you have to play games to put the N channels in the high side. All right. So that's all I want to do for that. And let's see. So I'm just going to say a couple things about H bridges. Not much. I'll probably let you go really. So H bridges are actually very, very complicated devices. Not so much because they're complicated to build, it's because when you control these big inductive loads, it gets complicated. It's the inductance that cause all the problems. And so there are two basic ways that we run these things, and neither one of them makes logical sense. So what you might think we would do, we don't. And so if you just took an H bridge and didn't read anything and you just started hooking it up, you'd probably hook it up in a way that would be bad, because it's not logical how they work. And only after you finally get beaten up a little bit, you realize, okay, I give, let me read and figure out what's going on here. Because this inductive load causes lots of problems. So that's one of the things that's tricky. All right. So the two ways we run these are called, one is sine magnitude and the other is lock anti-phase. And normally we do lock anti-phase. In this day and age, we pretty much only use H bridges with microcontrollers and PWM control. And it's really nice, works great, and it gives us the tremendous advantage of being able to run things at a whole range of RPMs and still get them to run and not stall out. Now, if you take a big motor, and you put the positive and the negative in, and you take this to ground, and then over here on the positive, you have a big rheostat, and you change this so that you're dropping less or more voltage across this resistor, then you can change the speed of this motor. But as you change this rheostat, you'll get to the point where you're dropping a lot of current across the resistor and the motor stops running. So you won't be able to run that motor really slowly. Way before you get to that point, it'll just stall, because there won't be enough voltage in its magnetic coils to make it go around. Well, with H bridges and PWM, we don't have this problem, because we're either turning the motor fully on forward or fully on backward all the time. And as a result, it has the sufficient torque to actually move even at very low speeds. So I know a bunch of you probably have battery operated drills. You can hold that trigger and get that battery operated drill to barely turn, right? That's only possible because of PWM. If you didn't use PWM, you could never do that. And in the old days, when I was a kid, we didn't have drills like that. The drill was either on or it was off. There was no in between. And there was almost no way to get the in between, because the electronics to get the in between was so expensive, nobody had it. So nowadays, it's amazing. So here's a standard H bridge, and they really are pretty straightforward. You basically have a load here, typically a motor, and you have 1, 2, 3, 4 switches. You have a high side motor power up here and a ground down here. Your motor power is usually 12 volts, 24 volts, for industrial purposes, 400 volts, who knows? All sorts of crazy voltages. And then you have usually electronic switches here. One here, one there, one there, one there, 4 of them. And they usually have a control line that goes to a microprocessor. Now, in all reality, these are usually also opto-isolated, and they're not BJTs, typically they're FETs. But in any event, this is just to give you an idea. And so what happens is, with this H bridge, you have the tremendous advantage of being able to run the motor either direction. And if you use PWM on these switches in just the right way, you can run it either direction at a whole range of speeds. Now, the basic function of it, and I'm not going to cover it all, I think I'll quit in just a minute, but I want to do the basic part here. In the basic function, there are really two main things. You basically have it set up, you turn on this switch, you turn off this one, you turn off this one, and you turn on that one, and you get the current to flow through this switch, through the motor, through that switch, and out to ground. and now it's running forward. Now you turn off these two switches, turn on these two, and we get the motor to run the other direction. But this is basically full speed forward, full speed reverse. To get it partial speed, that's when you have to PWM this. And that's where you have to get a little fancier. What you don't want to do is you don't ever want to turn on, well, and you also, because you have to have a pathway for backing, you have to go, you put diodes across these switches, and then what you don't ever want to do though is turn on this switch and this switch. Because now you have your high voltage supply shorted straight to ground through high powered switches, which means you're going to get a lot of current and you're no doubt going to burn something up. For sure you're going to blow up your switches, and you may cause a fire and burn down the building. So that's something you want to avoid. Okay, I think I won't say much more than that. Maybe I'll talk about this briefly at the end of the course. All right, we'll see you in lab.